Okay, let's continue our discussion on metric spaces. So the next topic is open and closed sets, right? Now to get some idea behind this concept of open sets, let's look at how we define the limit and then continuity of a function at a point, right? Hold on. So, how do we define continuity at a point of a function? Let's say a function defined on the set of real numbers, right? This is a real valued function, right? And then the limit of f of x as x tends to a, right? So the way we define this limit is that we say that for all epsilon positive, there is a delta positive such that 0 less than the modulus of x minus a less than delta implies the modulus of f of x minus f of a. Sorry, not f of a, right? Now we'll say that this is a good typo, not a mistake. So this is L, right? So first, so this L is a real number, right? So the modulus of f of x minus L less than epsilon. Okay, now one thing is that when we generalized the notion of distance, right? We looked at the modulus, right, of real numbers, all right? So, and then how do we, okay, now, first of all, we have this 0 less than, right? So here we exclude the point A from consideration in this, right? So what this says intuitively is that as you approach A, right, you get closer to A as much as possible, right? And then f of x gets closer to L, right? So in this notion, it doesn't matter whether the function is defined at A or not, and the value of f of A, right? But if you take the concept of continuity, right? So we say that the function if is continuous at A, right? If, right, now in this case, if has to be defined at A, and not only that, as x approaches E, right? The modulus of, so the f of x approaches f of E, right? Not some real number L which may not be equal to f of A in the case of limit, right? Continuity. So the function is continuous at A, right? Okay, now here in this continuity definition, A is included, right? Now let's look at the sets involved in this definition, right? So here, so A is a real number, and we are on the real line, right? So this is actually an interval minus the point A, right? So let me use a different color. So this is A, and here we have A plus delta, A minus delta, and here the point is not there, right? So you had actually, it's a circle, right? Circle, so that point is not included, and like this, right? But in the case of continuity, right, it is, so we have this interval, right, including the point A, right? And then if we consider, if we discuss these two concepts, limit and continuity, for a real valued function on R2, right? Then what are the corresponding sets, right? So now these X and A are points of R2, right? So the A could be like this, right? And then the set considered here. So what is this set? It is actually these all the points enclosed in the circle of radius delta, except the center 0, right? So the center 0 is not included. So I don't know. So we can extend this notation, right? So here I'm going to shade it. So this is set, right? Now if you take this set, right, for this function from R2 to R, right? So here, all the points, including A, are included, right? And then what about these two concepts? Concept of limit, the concept of continuity, right? In the case of a function from R3 to R, right? Now, I'm not going to draw these sets, right? So you can see that in the case of the limit, right, it is all the points enclosed by a sphere except the center A, right? So the as in the case of this interval and this disk, right? So the circle is not included, and in this case of the function R from R3 to R, the sphere, that shell is not included, but inside is included all the points except the center. In the case of continuity, all those points plus the center are included, right? So then I think you can see that these sets, right, which take the form of an interval in R and they take the form of an disk on R2 and the form of a sphere in R3, right? And then this definition should make sense that if we're going to study the concepts that that the concepts that have been formulated in real analysis, complex analysis, right? If you're going to study them uh, in a general setting where we have a set X equipped with a notion of distance, a distance function, then it is not surprising that the mathematicians have come up with this concept, right? Where the open ball with radius r and center x, right, denoted by this notation, right, b, and if we want to mention the metric, we put the d here as a subscript, x is the center and r is the radius, right, is this set, right? All the points within an r distance of x, right, including the center. And then we have this closed ball where we include the in the case of our example, the R2, the function from R2 to R, so where there we have a circle, we include that. And in the case of R3, we include the sphere, the surface. And in the case of an open interval, right, the endpoints. So this is the closed ball with radius R and center X, and denoted by this. And you will see, you'll make sense of this notation bar above it, right, to be to be understood, to be made sense later, right? So this is the set of points which are within r distance, including r from x, right? So when no confusion arises, we write like this, right? Okay. We don't write d, right? When actually we know what the metric we are referring to. All right. Now, to make more sense of these two concepts, open ball and closed ball, we have to do some exercises, and you have here some exercises, right? So these exercises, right, routine tasks, right? So you should actually pause this video and work this out before you continue, right? Pause and continue a little later, right? So this is such a moment, right? So let me also pause this and take a walk and come back, right? And then we'll continue with exercises, right? Okay. Okay, let's continue. Now, before we continue, let's note that when I try to motivate you for this concept of open balls, right, I considered the modulus, right, on R here, and then when it came to a function, a related function on R2 here, the Euclidean norm, right? And then when I considered a function from R3 to R, again the Euclidean norm, but we can consider any of those distances that we discussed in the early section, right? But then this interval, and then this disk, open disk, closed disk, they actually go with the Euclidean norm. Okay. All right. Now let's do this exercise. So we need to find the open ball with center 0 and radius 1 and the closed ball with the center 0 and radius 1 in the following metric spaces, right? So let's do that. So in the Roman 1, the metric space is the set of real numbers equipped with the usual metric or the Euclidean metric, right? Yeah, I said that usual norm, Euclidean norm. Yes, these are non-vector spaces, right? R2 and of course R3, right? They are non-vector spaces. And then the metric that we consider, Euclidean metric, is the metric which arises from the Euclidean norm, right? All right. So we don't talk about non-vector spaces in this course, right? We talk about Euclidean metric, right? So so in R, the open ball with radius 0 and center 1, of course, is an interval with center 0 and endpoints 1 and -1. And if you want, we can depict it like this, right? And we have to put a circle here to say that endpoints are not included, right? And what is a closed ball? So this is the open ball, right? And the closed ball is the closed ball is the same set with the inclusion of the endpoints, right? So that's closed ball, right? All right. Now, if the metric space is the set of real numbers with the discrete metric, right? So these discrete metric, and here the Euclidean metric. Euclidean metric. And this is the discrete metric. Right? So what is the open ball with radius 1 and center 1? Sorry, radius 0 and center 1, right? So these are the points x, such that the distance between x and 0 is less than 1, right? And so this is a discrete metric. So therefore, the distance between any 2 points is either 0 or 1, right? So you can see that this is actually just a singleton set, right? This is a singleton set. So you can see that so the open balls can vary, right, dramatically, right, depending on the so this is actually the open interval with sorry, it is open interval with the endpoints -1 and 1. Here it is this closed interval -1 and 1, right? But here the singleton set. And what about the closed ball with center 0 and radius 1? So this is the set of x's in R, right? And the distance between 0 and x is let's now equal to 1, right? And now you see that So 0 or 1, so it is 0 when x is 0, and it is 1 when x is any other point, and all these points are included, and you can see that the open ball is the whole of R, right? Now, I said that they can be dramatically different, right? And you can see that, it's, of course, dramatically different, right? Because in the case of the Euclidean metric, it is the closed interval with endpoints between 1 and 1. And here, the whole set of real numbers are, the whole set are, right? So this is kind of generality that we have to consider in order to have deeper insights into the concepts that we have already come across in real analysis and complex analysis, right? And the mathematicians embrace this kind of generality. They do not shy away from this kind of generality, right? They embrace it, right? Right. So there is exercise 1. Let's do the exercise 2. So in exercise 2, I guess the same exercise, but now it is in R2. Right? Okay, so in the case of R2, what is the open ball of center, the origin, and radius 1, right? So it is the set of all these points or vectors, but the points on the circle are not included, right? So this is, so let's go with the vector notation, right? X, such that distance, so this is the Euclidean metric, right? The distance between 0 vector and the vector x is less than 1, right? If you like, we can actually use the norm, right? So this is the norm of the vector x, and that is less than 1, right? Now, this could be, yes, so so this is fine, right? And then what is the closed ball? Closed ball would be the open ball plus the circle, right? So this is B, the open ball with the center origin and the radius 1. As I mentioned, when we type, we can put the bar on the top or the bottom, right? I think both are used. And what is the closed ball with center 0 and radius 1? So you can see that this is the set of vectors with norm, right? Less than or equal to 1, right? Okay. And yeah, then we have yeah, to figure out the open ball and the closed ball with center 0 and radius 1 when D is the square metric. And third part is that D is the taxicab metric, right? So if you remember, the shape of the unit circle in the square metric was given previously in the note, right? So it is this one. So 1, -1, 1, -1, right? So let me use a different color. So it is this square, right, with the you know that, so it is shaded, but the square is not included, right? So so this is so as vectors, right? This would be so this here the square norm, right, is less than 1, right? So if I go with these with the coordinate x1, x2, right, then this means that the maximum of the modulus of x1, the modulus of x2, so this is less than 1, right? So you can see that this is the set of um, points where the coordinates x1, x2, right, are between -1 and 1, right? You can write like this, right? If no confusion arises, right? So as a Cartesian product, we can write this one as -1, 1 cross -1, 1. The open intervals, right? Yes. And then what is the closed ball with center 0 and radius 1 in the square metric? So this is this Cartesian product, right? Okay. And then what about the Roman 3, right? So Roman 3 is that Roman 3 so if you remember, the unit circle in the taxicab metric is a diamond, right? Like this, right? So let's use the green color, right? So this is 1, -1, 1, -1, right? So what is the open ball with the center, the origin, the radius 1? So this is so if we go with the coordinates x1, x2, right? So this says what is the taxicab metric? So we take the sum, right, of, so it is the modulus of x1 plus the modulus of x2 less than 1, right? So we can see that when x2 is 0, right, we are here, and x2 is 0 and x1 is 1, right? So this is 1, 0, right? And this is 0, 1, right? And this is -1, 0, right? And this is 0, -1, right? And all these points are included, right? So you can give more, um, you can describe this set without these modulus, right? I'm going to leave it to you. And what is the closed ball? So this one is, so the modulus of x1 plus the modulus of x2 less than or equal to 1, right? So if we consider the diagram, right? So this outer diamond is also included, right? So now I believe that you have a good understanding of the shape of an open set and a closed set, and also why we define, why we have this concept of open set and closed set, right? And in the next definition, you will see that we need more definitions, right? More concepts, right? So that we can consider, we can talk about the concepts of limit, continuity, right, in a general setting, all right? Okay, before we continue, right, I want you to look at this definition 6 and make sense of this as much as possible, right? And then when I explain these concepts after so many years of experience, right, I think you should be able to make sense of these concepts, right? So let's take a break and continue, right? Okay, let's continue our discussion. Now, to make sense of this definition 6, there are several concepts there. To make sense of some of these concepts, right? Let's look at some example, right? Now, if we take this function f of x, let's say so it is a function. So it is one if x belongs to this open interval, right? So this is a function defined on defined from the interval 0, 1 into real numbers, right? It is not defined on R, right? Now, even though this is not defined at 0, right? We can talk about the limit of the function as x tends to, well, we can't say as x tends to 0 because x can tend to 0 from left and right. Now, on the left, we have negative numbers, and on those numbers, this function is not defined. So therefore, we have to say that we approach 0 from the right. So we put a plus here, right? So what is this limit? It is actually 1, right? And you can see that same way we have the limit as x tends to 1 minus f of x. And this is also 1, right? Now, what are these 0 and 1? What is the relation between those points, 0 and 1, with this interval? the open interval 0, 1, right? So here's the here's 0 and 1, right? And here's this open interval, right? So here circle, here circle, right? Now, what is the relation between the point 0 and 1 with the open interval 0, 1, right? So looks like these points are in a special relationship between with the set open interval 0, 1, right? Okay, and then I'll give you another example. So this is example number 1, and this is example number 2, right? So let's take a function, right? So f is defined as 1 if x is less than or equal to 1 and x is greater than or equal to 1, right? Here we should say O, right? So O, right? And then it is 2 if x is equal to 0, right? Okay. So if we draw this graph, the graph of f, right? If we draw it, it looks like this. So here is 0 and here is -1 and here is 1, right? So here is 1 and here is 2. So at 0 it is 2. So let's draw a point there, solid circle. And then here, circle. Nope. Again, a dot. I mean, so this is included, right? So like this, right? Now, the question is f continuous at 0, right? So f is continuous at 0 if we can get object close to 0, right? And then the function values get object close to 2. But there's something particular about this 0, right? Because the function is not defined, right? Defined, so not defined on in this open interval and this open interval, not defined, right? So as a result, right? So given any epsilon, right? We have this delta, right? What is this delta? So this can be satisfied. There's a delta such that this is less than delta implies the modulus of f of x minus f of 0 less than epsilon, right? So if you take this delta to be half, right? So here we have to say that, so this, okay, this and x belongs to the domain of f, right? So we can take this delta to be half, right? Then what happens? So what is this set x minus 0 less than delta and x belong to the domain of f, right? So this set is actually, right, we have only one point in this set, right? So if we write this as a set x such that this, right, and this set is simply the singleton set containing 0, right? So if this is just one singleton set, right? So at 0, of course, this is satisfied, right? Because you get, this is the modulus of f0 minus f0, right? Which is 0, right? So therefore, this function is continuous at 0, right? But this 0 seems to have a special property, right? And now, what is the relation between these examples and the definition we are going to talk about? So you will see that this 0 is an isolated point. Hold on. Okay, sorry about that. So 0 is an isolated point, and here 0 and 1 are limit points. Now, maybe at this point it doesn't make much sense, right? So let's go over this definition 6. So it has many concepts. So I think we need more space. So we'll bring this to somewhere with more space, right? Right. So the first concept is interior point of a set, right? So what's the setting? We have metric space and we have a subset of X and a point subset S of X, right? And a point X naught of X, right? We can draw a figure just to help us see what's going on, right? And here we have a set S, right? Like this, right? And a point X naught. So X naught is a point in X, right? So it could be anywhere in X, right? Right. So we call X naught an interior point of S, right? So there is this, if there is R positive, right, Bx naught comma R is contained in S. So make a picture of it, right? And that you remember, right? Don't remember, there's R, right? Be positive. No, this says that there's an open ball centered at the point X naught, and this open ball is contained in S. So such a point we call an interior point of S, right? So interior means that inside, right? Not exterior, right? Or not on the boundary, right? Interior, inside, right? So for a point to be interior, there has to be more points surrounding it, also in the set. So what better way to express this concept by saying that there's an open ball centered at the point, and this open ball is contained in the set, right? So once we define an interior point, then we can also define the interior of S, right? So it is simply the set of all interior points of S, right? So we denote it by this notation, int, right, S, set of all interior points of S, right? Now, the best way to make sense of this is to do some exercises, such as this exercise 3 given here, right? First, I will go over these concepts, and I did discuss two functions and two special points, right? All right. And then we call X naught a boundary point of S, right? Again, there is this with the quantifier, right? If for all R positive, B X naught R intersection S is not empty. So the way I make sense of this, there's an and also, and. So this and this, right? So the way I make sense of this is that, so here it is a boundary. So then the boundary in the normal language comes to my mind. So here I have a plot of land, 9 purchases, a rectangular shape, and I have a boundary. So on the front, I have boundary wall. Yeah, actually, and on one side, the blind wall. Yeah. So what is what is the property of this boundary wall? So boundary is like no man's land, right? So with a little movement, you could be inside the inside or outside, right? Inside means that in my plot, outside means that in my neighbor's plot or on the road, right? So can we use that to define a bound point in the general setting? And I can see that it is exactly what this definition does, right? So this is that, right? If you take the open ball with the tiniest radius, right? doesn't matter how small R is, it has a point inside S. So that's what it says, right? And this says that doesn't matter how small this open ball radius is, it has a point outside S in the complement of S, right? So that is a boundary point. And then if you take the set of all boundary points, right, it is a boundary, right, of S, right? And the boundary of my plot, 9.6 plot is the perimeter of this rectangle, right? So likewise, we can define the boundary of the set S, and it is denoted by this notation. I think this is a Greek letter daba, right? So interior point and the interior, boundary point and the boundary, and then the limit point, right? So it is a limit point of S, right? If all are positive, this is intersection is not empty, right? So that is actually the open ball except the point 0, right? And they have a point in common with S, no matter how small R is, right? The way I understand is that, so you have this point X node, which could or could not be in S, right? But we don't care because we can get close to this point, close in terms of the metric from the points in S, inside the points in S, not outside, inside the points in S, right? It is S. So this intersection, right, we call this the deleted, the open ball with the center deleted, right? So it intersects S, no matter how tiny R is. So that's a limit point. And now you have to go back to that example, right, that I discussed earlier, right? So I'm going to give you time, suppose, right? Go back to that example and see whether it makes sense, right? All right. Okay, let's continue. So hope you revisited that example, right? And why 0 and 1 are limit points of that set, the open interval with endpoints 0 and 1, right? So as I said, I interpreted, I have this picture of the limit point. Is a point may or may not be in the set S, right? And then we can approach this point through the points in S arbitrarily close. So such a point is called limit point. And the set of all limit points is called the derived set of S. And we can denote it by this notation, right? Is all the set of all limit points of S, right? And then we call x naught an isolated point if x naught belongs to S and not a limit point. So it is a point of S and not a limit point. So that means that there is R, right? Such that this this open ball with the center deleted, right? Open ball with center x naught and radius R, right? With center deleted, right? Has no point in S, right? Has no point in S. So now this is a good point to pause and go to the second example, right, of that function we discussed, right? And then I said that 0 is an isolated point, right, of the domain of F, right? 0 node is an isolated point of the domain of F. So where's that example? It is here, right? Isolated point of the domain, right? So the function is not defined on the open intervals with endpoints negative 1 and 0 and 0 and 1. It is defined on at 0. So as 0 is an isolated point of the domain of F, right? So take your time and understand this concept, right, of an isolated point, and then look at this definition, right? Where is it? Yeah, here. Right. So X node is an isolated point of S, right? If it is a point in S, it belongs to S, and it is not a point in the derived set of S. It is not a limit point of S. So this means that there's an open ball with center X node and some radius R with the center X node deleted, and it has no points in S, right? No points in S. Okay. So the isolated point is the opposite of the limit point, right? So limit point has so many inside people closer to that point. But the isolated point, there are no inside people anywhere near that point, isolated, right? All right, and then what are the other concepts? So we have the closure of S, right? And we denote it by putting a bar above S. Now recall our notation for the closed ball, right? So we put a bar here, right? So S closure, it is denoted by S. It is actually defined as S union S prime, S and its derived set, right? And then you have to make sense of why we have a bar here, right? The closure of S, and we call S is open, right? So now, earlier we had open ball. Now we call a set open, right? So open ball and open set, right? So we call a set open if S is equal to the interior of the set. And then also we have now S closed, right? So closed S, so closed ball, right? So we have to see, we have to make sense of the use of these words, open, right? So open set, open ball, closed S, right? So we call a set is closed if the boundary is contained in S, right? So we have to make sense of the remaining concepts in definition 6. And for this, it is a must that you do this exercise, right? So do the exercise 3 before you continue. All right. All right.